Hello, my friends. In this video, we are going to talk about the magnetic field somewhere above a circular conducting ring. In the last video, we have already learned the magnetic field just right at the center of a circular conducting ring. Suppose your conducting ring contains the column I, uh, and this is the little segment, and this segment is dB, dl, and the current running here is I. And we have learned that the magnetic field right at the center is given by uh, mu I divided by 2A. So what we are going to do today is to extend our analysis. Instead of observing the magnetic field right at this point, we are going to measure the magnetic field somewhere at some height above the metal ring. So now let's assume the radius of the radius of this ring is always A, and now let's assume the height is H. So we are going to detect the magnetic field at this point, observation point A. Before going on further, we have to analyze what we are going to get at the end of the calculation. If you have a magnetic field here, if you have a little current segment here, you will generally say um, you will generally say a magnetic field by Ampere's law. Um, the magnetic field should be heading, let's say, course B. It should be heading somewhere. Let's see. If you have a magnetic field here, then um, I is here. So you're going to have a magnetic field pointing this way, pointing this way. And likewise, if you have a magnetic field, if you have a current running along the whole circumference, you should expect another magnetic field on the right side. Uh, so you have a current here, and you also have a delta L here. And this delta L will end up with another magnetic field uh, running in the opposite direction. So you also have got a dB here. Uh, So at the end of the analysis, you should expect the horizontal contribution of this delta magnetic field will be cancel off with each other. So there shouldn't be any dBx minus dBx. There shouldn't be any. And at the end, you only end up with dby. So let's write down uh, what we are going to expect. Uh, dbx will be 0, will be cancelled off. Now, before going on further, right, we need to understand um, how this will look like. Now, um, this is the three-dimensional diagram. It's very difficult to interpret using the three-dimensional diagram. So why don't we just consider the Vy plane only? So let's redraw the experimental setup, and we are going to consider the Vy plane. So if you consider this Vy plane, then you will have a metal ring here. The metal ring will appear as appear like this, yeah? Because you are now looking at the horizontal direction. And then the current on the left side should be going into the plot. And the current running out of the plot. The current on the right side should be running out of the plot. And we are going to measure the magnetic field contribution. And now, so this is the I, and the delta L is a invisible section when we consider this plane only. So, right, we put delta L here just to remind us we are considering this here. And then suppose we are now considering right here H. So the height here will be H. And the length from here to here will be L, will be A. And the distance between this delta L and the observation point A can be calculated by Pythagoras theorem. So the length here should be A squared plus X squared and square root of the whole square. So this is the fundamental setup. And how are we going to get the magnetic field? Now, first of all, because in the right side, delta L is essentially a segment like this. And uh, assuming that uh, this red marker is the delta L, and the cap of the red marker is the arrowhead. The arrowhead, yeah. And then there's another one here, so the opposite side, like this. So now, what are you going to get for the current? So now it's pointing this way. So if we consider this point as a source of current going in, and the length here is like this, right? It's also square root of A square plus H square. So the easiest thing is to draw a circle and assuming that this is the length. So you're going to expect the magnetic field delta B pointing this way. And the angle here will be right angle. So BB will be here. And uh, this is another delta L. So if you can have a magnetic field due to this delta L here pointing this way, you should expect another one counterbalancing, uh, counterbalancing this delta B on the right side because of the fact that you have a delta L here. So again, I have to emphasize it's going to be the right angle. If it is not a right angle, then this means something wrong. So now, what is the question is what is the vertical magnetic field, the vertical equivalent for the magnetic field, right? The vertical equivalent, the vertical magnetic field should be dBy, yeah, dBy. So better write this down, dBy. So now, let's assume this angle as alpha, and by inspection, this angle is going to be 90 degrees minus alpha. So the first thing that we need is to find out the expression of delta B. The second is the second thing that we need is the second step that we need is to work out the vertical equivalent of this magnetic field dP. Okay, now let's start from here. We don't need the three-dimensional diagram. We don't need the three-dimensional diagram. So now we need to find the magnitude of delta B. According to what we have got here, delta B is magnetic field dB, and delta L from a right angle with each other. Because right, the delta L at this segment is pointing outward to right one. Well, where the magnetic field, I don't know whether I should say this. The magnetic field is pointing, dB is pointing this way. I think this is right, yeah? So the dB is pointing this way. Okay, let's write this down. So now, according to the diagram here, dB and dB are orthogonal with each other. So better write this down. dB and dL are orthogonal with each other. So in this case, if it is the case, then we can write down here dB is equals to mu I for pi. And then this expression will be multiplied by um, delta L divided by the length here is a squared. Uh, length, yeah. The length should be this one, right? So it should be a squared plus h squared. And uh, then sine theta, sine theta. Theta is 90 degree anyway. So this is the length, right? Uh, so 90 degree will be 1. Sine 90 degree will be 1. So eventually delta B will end up being delta L divided by square plus h squared. H is the height of this observation point. It's not going to change. A is the radius of this metal ring. It's not going to change. Uh, so what is changing is L. And the question is uh, L. L is the length measured along the circumference. So we are now going to work out the magnetic field. Uh, and the magnetic field for the total magnetic field dB, B, B is pointing this way, right? I'm not considering is integral of B. The integral of B is given by mu I for pi. And then the integral should start from here. For instance, if we are going to start from here and we become dB in here, then we should start from 0 until 2 pi L, 2 pi A to 0, 0, and then 2 pi A. And then DL. So eventually, uh, sorry, you have to, we have to write down this one as well. This one is not going to change. So I have to write this down. And then DL, right? So we don't need the, yeah, we show what we understood this page. So we're going to write this down. Y, Z, N. So it's 0 to 2 pi A D L. So eventually, what we are going to do here will be um, will be equals to mu I 2 pi A divided by 4 pi a squared plus x squared. And the pi will cancel off with each other. So you will end up with more pi and 2 here. And, and, and as I already said, the horizontal equation for dv will be 0. The only magnetic field that is available will be in the vertical direction, z direction. And this vertical direction will be dy. This magnetic field in the vertical direction will be dy. And then b, uh, cosine of this angle, 90 degrees minus theta, which is equal to b sine theta, sine alpha. And what is sine alpha? The this one divided by this. So I'm going to write down here b sine is a divided by the square root of a square plus x square. And if it is the case, if we substitute the variable b into this expression, we are going to get mu I a we have a square, and then 2 a square plus x square, and then to the power b divided by 2. So this is the answer. The total magnetic field will be pointing upward in the z direction, and the value of this upward magnetic field will be given by mu I a square divided by this value. If if x is 0, then eventually, right, if x is 0, then the magnetic field By will be equal to mu I divided by 2a, which is exactly the same uh, as the answer we got from the previous video. So now the proof has been established. This is the answer. Thank you.